Welcome to the anticipated section 5.3, where we're going to now deal with equations. So we're not just verifying the using the identities, we're now going to actually solve for x. And a couple things I want to highlight. One, when you're working just as with any equation, you want to isolate the function. Get the sine, cosine, the trig function usually on one side of the equation, or you need to factor it so that you can solve for both answers. You may factor or use the identities. That's why we've been practicing this for 2 sections, so that they are now common to you and you have those down so that you can now apply them. You're going to give exact solutions. That means no decimals. All your answers are going to be in pi. You are going, except for some applications, right? But most of the time, your answers are in radian value. Sometimes you can graph both sides of the equation and then obtain the intersection, which would be your solution. Now, I caution you to doing this because you don't always have access to a calculator, and you need to learn how to manipulate the equation to achieve the answer rather than picking up your calculator and just graphing it. I do want to remind you that you need your good old unit circle. You've got to have that down. Excuse me. I brought out mine, and I want to review this with you. Very quickly, you need to review, obviously, that cosine is x, sine is y, and you need to really have down these values out here, the coordinate points. Also, that at pi over 3, your tangent is square root of 3, and your cotangent would be square root of 3 over 3. And then likewise, there at 30 degrees, at pi over 6, that's flipped. Your tangent is square root of 3 over 3, and your cotangent is square root of 3. And remember that cotangent at pi over 3, that value is the same down here for the tangent at 4 pi over 3. In quadrants 1 and 3, tangent, cotangent are positive, they're negative in 2 and 4. All this is review. All this you need to have memorized and bring back to the surface. I know you've been pushed it back into your brain for a while. We're going to try 2 examples here. I would like you to copy these down, and we are going to solve these equations for all values of x. That means you can get the normal answer that you would just get initially, but then we're going to...
Teachers, you may now...
Sorry for that interruption. But we are going to solve these for all values of x. That means once we get where it is on the circle, we have to account for spinning around and around and around and around the circle. Let's just play with the first one. The first example says 2 cosine x plus 1 equals 0. So if I move the 1 over, divide by 2, I have cosine x equals negative 1/2. Well, I want you to think about where that happens on the circle that we just talked about. And that happens, if you think about where cosine is negative 1/2, that's up here and down here, right? So that's at 2 pi over 3 and 4 pi over 3. Now, if you notice, they are not right across the unit circle from each other. So if I want other answers here at that point at the 2 pi over 3, I have to go all the way around, come back around. I have to go all the way around the 2 pi of the circle. So when I'm writing that answer that could be at 2 pi over 3, I'm going to say I'm at 2 pi over 3, but I have to add multiples of 2 pi because that can kick me around to that same spot. I could also be at 4 pi over 3 down here in quadrant 3, and I would need to be, I could also have multiples of 2 pi. So I have 2 equations for answers. Okay, this is to, again, to get all the values of x, any x. So if I let n be 0, then I'm just at 2 pi over 3. If I let n be 1, then I would be at 6 pi over 3, I would be at 8 pi over 3 right there if I spun around the circle again. And I can add any multiple of n to get all the possible values that would land right there. And likewise for 4 pi over 3. Okay? So these, the 2 pi over, or multiples of the 2 pi, those allow for coterminal angles. Let's try another example. This one says 3 secant squared x minus 4 is 0. So move the 4 to the other side, divide by 3. You're going to have secant squared is 4/3. If I just want secant, I need to take the square root. And so secant x, if I take the square root of that, I need to account for both positive and negative. It's going to be 2 over the square root of 3. Square root of 4 over the square root of 3, that's 2. Now that's secant. And you don't necessarily remember all the secant values on your circle, but you do know the reciprocal of secant, which is cosine. So I would flip that. Cosine of x is going to be all values of square root of 3 over 2. That one we do know. All the positive or negative square root of 3 over 2 for cosine, that happens at all the pi over 6's, doesn't it? Okay, if I were to sketch that out, that would happen here, and here, and here, and here. It happens everywhere on those pi over 6 values. But when we write the equations, we don't need to write all 4 of them on the unit circle and then say add multiples of 2 pi. Because if I just write this one at pi over 6, if I add a multiple of pi, I'm going to end up here. If I add a multiple of pi, I'm going to end up here, and then a multiple of pi, and here, and it spins around on that line. So I'm really only giving that point and in quadrant 2. And I'm going to say adding a multiple of pi instead of having to list all 4 equations. So my first one would be at pi over 6, and I'm going to add, as I said, a multiple of pi because that will swing me around into quadrant 3. And then I can also have 5 pi over 6, which is in quadrant 2, and if I add a multiple of pi, half the circle, that's going to take me around into quadrant 4, and we'll pick up that answer. And then if I add pi, a multiple of pi again, that spins me around again and again and again. So I really only need those 2 values and add multiples of pi, and it encompasses the total 4 answers. And multiples of pi, you can get numerous, infinite answers, as a matter of fact, as much as you want to go around. All right, we are now going to solve a different type of equation. I'm going to set that up. The next type of problem we're going to do is where we are going to solve for all solutions on a given interval. Now, I will tell you that you will come to like these probably a little bit better because you're giving me specific answers on this interval. You're not necessarily giving me the equations that will get me all values of x. So you learned that this is a little simpler. It's a little bit easier to work with in some regards. All right, so let's look at example 3. 2 cosine squared plus cosine equals 1. I hope you recognize that as something that may be factorable. I'm going to bring the 1 to the other side, so I have 2 cosine squared plus cosine minus 1 equals 0. And that we can factor that. So I've got 2 cosine, cosine. The only way to get a 1 is with 1s. Now I've got positive 1 in the middle for my middle term, which means I need my 2 cosine to be positive, that one to be negative. Double check, negative times positive gives me my negative. I'm good. Now just like we've done with other solving of equations. Now you're going to take both of these and you're going to set them equal to 0. When I do that, I'm going to have 2 cosine x minus 1 equals 0. I hope you see that that means cosine x is 1/2. Okay, this one, if I set that equal to 0, I have cosine x is negative 1. Well, you got to think about where this happens. Where does cosine equal 1/2 on your circle? Positive 1/2. Okay, that happens up here at pi over 3, right? Okay, that happens when x is equal to pi over 3. And then down here in quadrant 4, that would be at 5 pi over 3. I always remember 6 pi over 3 would be 2 pi, so that's almost all the way around. Let's get this answer. Cosine is negative 1. Well, that only happens on my circle right over here at pi. So that's the other answer, is pi. So I have these 3 answers for that equation. All 3 of those would make that equation work. Let's look at example 4. Example 4 says 2 cosecant squared plus cotangent squared minus 3 equals 0. We have a little bit of work to do on this one, and this is where some of your identities come into hand. I have a cosecant squared and a cotangent squared, and I have to decide which one I'm going to keep. I know that I have a relation between them with my identities, my Pythagorean identities. I think I'm going to take this one out, and the reason is I already have a positive cosecant squared, and it has a coefficient. So instead of having to distribute that, I'm just going to replace cotangent squared with cosecant squared minus 1. When I replace that, let me go to a different color here. And that would give me then 2 cosecant squared minus 3. And now I can combine like terms. If I have 2 cosecant squareds plus 1 cosecant squared, I have now 3 cosecant squareds. And negative 1 minus 3 is usually 4. Now this is very similar to example number 1 that we did. So now I'm going to move the 4, divide by 3, and I've got cosecant squared is equal to 4/3. I'm going to take the square root, and that gives me that cosecant equals positive and negative 2 over the square root of 3. And remember, that's cosecant. We don't necessarily know where to memorize those on the circle, but we do have memorized the reciprocal of that, and that is sine. So I do know where the sine values reciprocate that would be square root of 3 over 2. That I know is at all of the pi over 3's, right? So that is all up here and down here, and up here and down here, right? All the pi over 3's. And I can just write those out. X equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. That's my solution set. When you come back in part 2, we will continue to work some examples. We're going to do one more example in this set, and then we've got one more type to do. Thank you. I'll see you then.